Maybe we should start. Yeah, it's a pleasure to introduce Caique Luko. He's a fourth-year PhD student at UC San Diego, and his research explores how ocean eddies and internal wave-driven mixing can shape marine ecosystems and influence climate system. In today's presentation, he will discuss how fine-scale ocean processes can intensify heat exchange at the surface of the ocean. And this topic aligns very closely with the focus of this seminar series, and I'm glad to give him the floor.
Thank you, Yuri, for the introduction. Thanks also for the invite to present here. I've been attending these meetings and watching recordings for a couple years, so it's really fun to be talking here. Um, so let me just turn on my pointer. So yeah, as Yuri said, I'm a PhD student at Scripps. I'm working with Professor Jen McKinnon and Amy Waterhouse. And today I'm going to talk about Submesoscale Salinity fronts and how they can alter SST, RCE fluxes, and vertical transports. I know this is a big title, but if you need to remember three things about this talk today, is that mainly the first one is that warm waters can converge as submesoscale salinity fronts and create narrow SST filaments. These, as a consequence for this, we're going to alter RC heat fluxes. And lastly, these narrow filaments also support downward vertical heat transport, which is the opposite of what's observed on temperature fronts. But before we get too deep into this, let's remind ourselves of what are mesoscale fronts and why they're important. The mesoscale fronts have length scales of hundreds of meters to tens of kilometers. They can be sometimes controlled more by temperature gradients, sometimes more by salinity gradients, and they're dynamically defined as fronts with Rossby number order 1. At these fronts, we observe strong convergence and strong vertical velocities, and this is one of the reasons the mesoscale fronts are important. There are strong vertical exchanges of biogeochemical tracers, of heat, nutrients, and dissolved gases at these fronts. For temperature fronts, for example, we also observe, we always observe an upward heat transport because of the alignment of the temperature anomalies with the vertical velocity anomalies. And this upward heat transport is responsible to restratify the upper ocean, controlling SST and ocean heat uptake. There are some global simulations that include this process, and it's shown that the inclusion of this process can warm up the sea surface by 0.3 degrees Celsius. Um, Besides the importance for vertical exchanges, temperature fronts also influence air-sea interactions. Lucy gave a talk 2 weeks ago here in the Southern Ocean, which was really interesting. And these maps here are from the same simulation that Lucy showed, but for the Kuroshio extension. And on the ISO lines, we have the isotherms, and in the color, we have latent heat fluxes. We can see that on warm waters, there's enhanced latent heat fluxes, and in cold waters, we have uh, weaker latent heat fluxes. And some of this variability is modulated by the temperature front. We can see that like the very sharp mesoscale fronts here can generate a strong variability in the latent heat fluxes. Besides affecting RC heat fluxes, temperature fronts can also affect wind stress divergence, and it has been shown recently that this can support enhanced convection and precipitation located at the front. So temperature fronts have all these, it's important for all these vertical exchanges and RC interactions, but what about salinity fronts? How can salinity fronts actually affect SST, RC heat fluxes, and vertical heat transport? So one of the first interesting thing about salinity fronts is that because temperature doesn't act a strong role in the dynamics, it doesn't really drive the flow. It can act a little bit more like a passive tracer, and we can end up with these very interesting situations where warm water subducts under cold water. And in a normal situation, this would be unstable, but because the stratification is controlled by salinity here, we can maintain this warm water under the cold water. These two vertical sections are from the Texas Louisiana Shelf. They were taken on the Sunrise 2021 cruise. And a year later, for the Sunrise 2022 cruise, we went there and we crossed some of these fronts and filaments once again. And because we had four assets, we were actually able to compute W with the plane fit method. And over a whole inertial cycle, here on this plot, we have time on the x-axis and depth on the y-axis. Over one inertial period, we measure the actual vertical heat transport at these fronts. And we see that sometimes it can go down to minus 500 watts per meter squared, which is as strong as RCT fluxes. And this leads to a cooling rate of zero point 0.2 degrees Celsius at the peak. So this is one way that salinity fronts can kind of revert the process of vertical exchanges. And a second way of how salinity fronts act different is that it has been shown that when salinity fronts are exposed to sea surface cooling, they can actually form cold filaments along the fronts. This is because at the fronts we have a shallower mix layer, and so the cooling is more effective on this shallower layer, and we end up with cold filaments. Consequently, this is also going to play a role in compensating the front, and will be important for the dynamics. Here, we actually want to study the opposite case. We want to study what happens to salinity fronts when we expose them to surface warming. And more specifically, we want to understand what happens to SST, to the RCT fluxes, and to vertical heat transport. To achieve this objective, the study region that we're going to focus in is the Texas Louisiana Shelf. We choose this region not only because we had data from the Sunrise cruise, but also because we have both ingredients that we need. We have salinity fronts that are created by the Mississippi Atchafalaya River plume, and this is a region that experiences strong warming during late spring and summer. The data that we're going to use is going to be a combination of satellite data, shipboard data, and numerical simulations. The satellite data that we're going to use is Sentinel-3. This is a radiometer-based SST sensor with a resolution of 1 kilometers and nadir, so we're capable of observing submesoscale signals. The shipboard data that we're going to use is from the Sunrise 2022 cruise, and we're going to use flow-through temperature and salinity data besides profiling data and the meteorological data from the ship. And lastly, the simulation that we're using is we call it the TXLA simulation, is a ROMS nested simulation run for the Texas Louisiana Shelf. This is a simulation run by Rob Hadland's group, and at the boundaries, it's forced by HICOM, and the atmospheric forcing comes from ERA 5. This nested simulation has a coarser grid or a parent grid, which has 2 kilometer resolution, and on the shelf, it's the mesoscale permitting. And there's also an inner grid, a child grid, with a higher resolution of 400 meter resolution of 400 meters. And this one is mesoscale resolving for the shelf. And so what do we actually see with the data? So starting with the satellite, so we started this analysis when we were going out on the cruise and we were trying to figure out our sampling plan. And we plotted the SST images and we were very surprised to see these beautiful filaments, these narrow SST filaments, much like the spirals on the sea observed by Monk. And at the time, we didn't really understand what was going on, but after staring at this for longer, we started to wonder if these filaments were collocated with the salinity fronts formed by the river plume. And as a first test, we took one of our transects. This is from when we left the port and were traveling to our sampling area. So we crossed a bunch of these filaments, and we checked if the filaments were actually matching with the fronts. And so here we're plotting distance in the x-axis, and on this first subplot, we have the sea surface density. We can see that along our transit, we cross a bunch of density fronts. These fronts are controlled mainly by salinity. We can see here in this panel, sea surface salinity, the shape of the curves are really similar. And panel C, I'm also showing the salinity gradients along the transect. So we can see a couple peaks where we cross the fronts. And when we look at SST, here the red is the the actual data, and the dashed is a running average with 20 kilometers to define the mesoscale field. And we can see that there are some anomalies, some submesoscale anomalies that align pretty well with the salinity fronts. These anomalies can be as strong as zero point 0.8 degrees Celsius in these observations. And so this was our first confirmation that the filaments were um, indeed related to the salinity fronts. And then how does this look in the vertical? This is from another transect. This is another day, another beautiful satellite image of a bunch of filaments. And we cross this swirling eddy here, kind of like on the edge of it. And when we look at the data, salinity, we can see this was an anticyclone because of the shape of the isopycnose. And it's fresh on the core, and it gets saltier as we move offshore. And at the temperature, we can see that there's some uh, warmer waters associated with these fronts. This becomes more evident if we actually plot the salinity gradient and the mesoscale temperature anomaly. Here's, for example, a front and some temperature anomalies extending to depth. Another front here and strong salinity gradient, and we can see these peaks in the temperature anomaly. And these are actually some mesoscale fronts. We plotted the Rossby number with the a long section ADCP data, and we see that these are some mesoscale fronts. So um, with the satellite data and the shipboard data, we confirmed that the temperature anomalies align with mesoscale salinity fronts. But to understand more how these filaments are actually formed, we shift to the model simulations. And for the model simulation, these are some snapshots of the sea surface salinity and the salinity gradient. We can see the Mississippi River plume and Atchafalaya River plume coming out and forming all these fronts along the shelf. Here's a view of the salinity gradient showing these very sharp salinity fronts. And again, these fronts are submesoscale fronts. In the child grid, we can see that they reach order one number. In the parent grid, they also reach order one numbers at some places, but we can see that the fronts are a little bit less resolved. And we were very happy to see that in the model, we actually also represented the formation of the warm SST filaments. And in particular, they're more intense in the child grid where we resolve more of the mesoscale activity. We can do a comparison of the two how the two different solutions differ, how they perform in representing the filaments. And so in these two different boxes, we computed joint PDFs of the Rossby number with the submesoscale temperature anomaly. On the left, we have the PDF for the coarser grid, and on the right, we have the PDF for the higher resolution grid. And what we see is that for the coarser grid, we have a smaller correlation and a smaller slope of the linear regression. And we see that there are not a lot of strong anomalies in SST uh, when we go to higher to cyclonic Rossby numbers. But when we compare with the child grid, the one that's submesoscale resolving, we have an increase in the correlation between the temperature anomalies and the Rossby number, and an increase in the slope of the linear regression, also showing more extreme SST anomalies for higher cyclonic Rossby numbers. And so this shows to us that we really need submesoscale resolving models to reproduce this kind of process. Okay, now how do the filaments actually get created? How are they formed? We're going to argue here that because we're in a salinity stratified region, temperature acts more like a passive tracer. And because of that, we're going to have an interplay between the 3D circulation fronts that's going to steer the vertical temperature gradient around, and it's going to form filaments. But we're also going to have a row of the atmospheric heat fluxes along the particle trajectories, which are going to sustain and amplify these filaments. And so to convince you guys that this is happening, we're going to use two methods. We're going to first do a heat budget, and then I'm going to show you guys a Lagrangian experiment. But first, starting with the heat budget, we integrate our heat budget in the first 2 meters of the water column. Reminder here that the water column here is 30 meters deep since this is on the shelf, and the mixed layer depth can be as shallow as 1 meter. So we chose 2 meters to represent the processes controlling SST. We also did tests with 5 meters and different depths, but there was not a lot of sensitivity to this. But in our heat budget, we have the tendency term here. We have the advection, the heat transport term. We have this term called which we're calling the vertical heat fluxes, which is the atmospheric net heat fluxes minus the mixing at the bottom. The important thing here, the process that I showed you guys in the introduction, the more effective cooling, where the mixed layer shallower is going to show up on this term. And then lastly, we have the horizontal heat fluxes, which is basically the numerical mixing. We computed the heat budget offline. So when we sum all these terms, they're not exactly the same as a tendency because we're using 1 hour time steps instead of the actual time step of the model. So when we sum all these terms, we're gonna call it the net. And what we're gonna do with this heat budget is that we're gonna redistribute each of these terms in Rossby number by time diagram. The way we do that is that for each snapshot, we're gonna bin average or heat budget terms to different Rossby number bins, and then we're gonna see what happens in time. The reason why we do that is because we want to see if any of these heat budget terms uh, generate some differential warming in the region where we have the Submesoscale cyclonic fronts. And so, starting with the VHF term, what we see is we actually see a very constant vertical heat flux diurnal warming and cooling across all vorticities. So this rules out the process by Amala and Gualtiero, where they had more effective cooling for the fronts where we have a shallower mix layer. Uh, and yeah, we see a very constant vertical heat flux across verticity space, and we have some variability in time. And this is explained by the wind speed. Basically, on low wind scenarios, we have a more well-pronounced diurnal cycle of this term. But when we have stronger wind speeds, the heat that's deposited on the 2 meters is mixed down, and we end up with a less intense diurnal cycle. It's also important to see that here the heating during the day is stronger than the cooling during the night. So these are periods where we're having a net deposition of heat over the day. Now let's move to the next term, the advection term. When we plot the Rodby number time diagram, we actually see that the advection term does generate differential warming at the fronts. We see these periods when there's a lot of warming diurnally at the fronts. And how does this look in a map if we take one snapshot? So this is a snapshot of the advective term. We can see that all these different filaments along the domain they're being warmed by the advection term. And how does this actually work? We can break out the advection term into convergence of horizontal heat transport and a vertical heat transport at the bottom of our layer. And this is what we see here. This is the convergence of horizontal heat transport, and this is the vertical transport. Red means convergence, and what we see is that the heat is converging at fronts and diverging outside of the fronts. And part of this convergence is balanced by the vertical heat transport that's transporting heat down outside of the layer. One thing that's important here is that these terms are we're only warming the fronts by convergence of heat because we have a temperature gradient. If we didn't have a temperature gradient, the convergence of heat transport would match exactly the vertical heat transport, and we wouldn't be warming the fronts. And this can actually be shown, this relationship with like the dependence of having a temperature gradient. If we compare to the to a rolling average of the vertical heat fluxes only in periods where we have a deposition of heat in the top layer that forms a temperature gradient. it's when we have the advection actually warming the front. So in the end of the period here, when we have this net deposition of heat, we have more of the advective heating. In the beginning too, when we have net deposition of heat in the top layer, we have the advective heating. And when we have the kind of like the negative VHF, we have these disruptions of the advective heating. So what's the whole story? Uh, the horizontal heat fluxes, they're negligible. So basically, we're going to have a sum of the VHF and the advection term controlling the heating in the shelf, and the net term is, you can basically see that is like a constant cooling and warming on the shelf and more warming at the fronts because of the advective term. I also plotted here the same kind of graph for submesoscale temperature anomalies, just to show to you guys that in the periods where we have the advective heating is when we generate more of these warm SST filaments. Okay, so we've learned that advection plays a central role on the formation of these filaments, but you gain more intuition on what's actually happening. How can the advection be warming the front? We're going to perform a Lagrangian experiment. And on this Lagrangian experiment, we're doing it offline, and we're using the OpenDrift package. This is a Python package that's easily coupled with ROM simulation, so that's why we choose to use this one. And in our Lagrangian experiment, we're going to release particles between 1 and 6 meters with a horizontal spacing of 200 meters and a vertical spacing of 0.5 meters. After we simulate their trajectories, we simulate their temperature and the evolution of temperature. And what we do is that for particles that are above 2 meters, we start them with a temperature of 32.5 degrees Celsius, and we evolve them forced by the atmospheric heat fluxes. And for the temperatures that are below 2 meters, we start them with 30.5 degrees Celsius, and they're not affected by atmospheric heat fluxes. These choices were made based on the model outputs. We did see vertical temperature gradients going like this, uh, separated around 2 meters. And the influence of the atmospheric heat fluxes also, the penetrative heating in the model was set to represent very brackish waters since it's close to river plume, and the region that's more affected by diurnal variability atmospheric heating is above 2 meters. So these values were chosen to match that. And we're basically doing this simulation to, again, test two things. First one is to see if the submesoscale flow can steer this initial vertical temperature gradient around and from the filaments. And the second thing is to see what's the role of the atmospheric heat fluxes along the particle trajectories. And so here's a video of the simulation. Let me just increase the quality and put it on loop. So we're gonna start here. We're gonna start with I'm only plotting here on the right the particles that are between 1 and 2 meters, and we have the initial condition with all the particles in the top with 32.5 degrees Celsius. And as soon as we start running the simulation, the particles quickly start to converge at the same regions where we see the SST filaments on the 3D simulation. And outside of the fronts, we have the cold water being upwelled. And superposed into that, we also have the atmospheric heat fluxes kind of like amplifying these horizontal SST differences. After 2 days, we end up with a scenario with warm filaments very similar to what we observed in the actual 3D simulation. And this is a very simple Lagrangian experiment showing kind of like the same behavior. I'll let it play one more time. Yeah. And so we pick some of these particles in different regions of the front. We have a set of particles that are at the warm filaments where we have the submesoscale front, and we also pick particles in a colder region where we're outside the front, and we check what happened to them over the course of a day. So here on the right, I'm plotting time at the x-axis and depth on the y-axis of the first subplot and temperature on the y-axis of the second subplot. The the end of the graph here is what's shown on the snapshot. And what we see is that like the particles that are at the front, they've been at the surface for a longer time. And so they were initialized with a higher temperature, and they've also been exposed to the atmospheric heat fluxes for longer. So you can see that they're warmer, and there's a diurnal cycle here that kind of turns them into like even higher temperatures at some than they were initialized. And then the particles that were outside of the front at the end snapshot, we can see that they were recently upwelled, and so they were colder. They were initialized as colder particles, and they have not been affected by the diurnal effluxes. So only when they reach that top layer they start being affected. So basically, this shows that the 3D steering of the particles generate the filaments, and that the atmospheric heat fluxes they maintain and sustain those horizontal SST gradients. Okay, so we've learned that the warm waters can converge at fronts at the submesoscale salinity fronts. Now, what's the consequence for the RC heat fluxes and for the vertical heat transport? So starting with the RC heat fluxes, going back to our big flow through transect, we have again the salinity fronts and the SST anomalies. When we look at the atmospheric temperature, we don't see a lot of changes in atmospheric temperature associated to the filament. But when we look at wind speed, we can see some wind speed anomalies that are associated to these SST anomalies. And these wind speed anomalies can be from zero point 0.5 to 1 meter per second, collocated with the warmer waters at the fronts. This is really interesting because we're having higher wind speed at a salinity front in a region where we wouldn't expect this, because usually the stronger wind speeds are observed where we have warmer waters, which doesn't necessarily always align with salinity fronts. When we look at the air-sea temperature difference, we see that there are strong air-sea temperature differences generated by these SST filaments, and we also have strong air-sea relative humidity differences happening at these fronts. And this is gonna translate to anomalies in sensible heat fluxes and in latent heat fluxes. Here, our convention is that negative RC heat fluxes means that it's out of the ocean. So we have these negative submesoscale anomalies of sensible heat fluxes. They can be of 5 watts per meter squared, and the latent heat fluxes they can be from 20 to 50 watts per meter squared. And again, we're getting anomalies of these RC heat fluxes in a place where we wouldn't really expect it, since it's a salinity front. Now, the model also represents the formation of these anomalies in RC heat fluxes. We have here the latent heat fluxes on the left and the sensible heat fluxes on the right. Again, they're more intense inside the child breed domain, since we have the more intense SST filaments. But here in the simulation, they're a little bit stronger than the observations. We have actually 100 watts per meter squared anomalies uh, for the latent heat fluxes, and 20 to 30 watts per meter squared in the sensible heat fluxes. We think that these stronger values are being generated in the model because it's not a couple simulation. It's so the way these fluxes are computed is just with the SST output from the model and the ERA5 atmospheric temperature and have relative humidity. So there might be a bias here because this is not a couple simulation. But we're really happy to see that the formation of the filaments happens for the RC fluxes here too. Now, what happens to the vertical heat exchanges at these fronts? So again, we showed in the observations and in the introduction other work showing that warm waters can subduct under cold waters in salinity fronts. This is also represented in our numerical simulation. We see all these submesoscale fronts along the shelf, and they align with the SST filaments and with the subduction of these warm waters. And this is going to have two main consequences. The first one is that this is going to generate variability. Spice is this quantity that measures along isopycnal variability of temperature and salinity. So when we have a positive spice, waters are warmer and saltier for that uh, isopycnal layer, and we call them spicier when they're warmer and saltier. When we have a negative spice, we have colder and fresher waters, and we call those waters minty. And so this process generates horizontal spice variability, and these spice variability is transported down at the subduction sites. And we see this both in the simulation and in the shipboard data. Now, SPICE is useful to understand water mass variability along isopycnals, but another important thing is that SPICE can set up the stage for double diffusive instabilities. So actually, the formation of these filaments and the subduction of warm waters can set up the stage for double diffusion to happen in these salinity stratified oceans. Now, uh, the second consequence for the vertical of the subduction of warm water is actually the vertical heat transport. Here in our simulation, we see downward vertical heat transport up to 2,000 watts per meter squared going down, uh, which is the reverse of what's observed in temperature fronts. And if we average this vertical heat transport along the shelf, we picked a 90 kilometers by 90 kilometer box. If we average it and see what happens in time, uh, that's the plot that I'm showing here, time on the x-axis and depth on the y-axis. This is a vertical heat transport average on the shelf. And here on the top, I'm plotting the correlation between Rossby number and the submesoscale temperature anomalies. This is basically to see times when we have more formation of the warm filaments. We actually see that the vertical heat transport is downward and stronger in periods when we have the formation of the filaments. And when it's averaged over the shelf, it can go the averages of about 40 watts per meter squared. And if we integrate this vertical heat transport over the month, the period of the simulation, we do see that the vertical heat transport is mainly downward and stronger for the child grid domain, the one that has higher resolution when compared to the parent grid domain. If we translate this vertical heat integrated heat transport into a change in temperature over the month, we see that the vertical heat transport in the child grid domain is responsible to uh, cool the sea surface temperature since the heat is going down, and to warm the subsurface by zero point 0.2 degrees Celsius. And actually, if we try to estimate what's the change in heat content, the subsurface heat content, which we define here as like below 7 meters, we see that for the child grid domain, we have an increase in subsurface heat content that's 2 times higher than what's generated by the parent grid domain. And this increase in subsurface heat content because of vertical heat transport actually accounts for 10% of the total subsurface heat content increase. Uh, so this really shows how this process is important for heat content evolution. Now, since we learned that these warm filaments happen and they're important for RC heat fluxes and vertical heat transport, it'll be interesting to know where in the world this process might happen. And so we do an analysis here to try to look for the co-occurrence of the two ingredients we need for the formation of the filaments, which is the net heating and the salinity-driven fronts. The way we do that is very similar to what Gualtiero and Amelet did. We're going to compute a parameter, the gamma parameter, which is the co-occurrence parameter. And it's basically a product between Q, which is the normalized net heating that we're taking from era 5. And this normalized net heating is going to be equal to 1 when we have a net surface heating of 75 watts per meter squared. This is our metric to say that we have a strong heating occurring in a region. And it's a product between Q and R. R is the normalized horizontal turn angle, which we compute from the World Ocean Atlas climatology. And when R is equal to 1, we have fronts driven by salinity. So when this product is closer to 1, it means that we have a co-occurrence of the two ingredients we need. And so we did that with the climatologies of this parameter. And what we see is that there are several different places across the globe where we have candidates for these filaments to happen. Mostly river plumes like the Congo River plume, the La Plata River plume, the Mississippi, the Bay of Bengal. These are all candidates for this process to happen, but also polar oceans, especially austral summer and austral summer and boreal summer. These are times when we have more ice melts and more salinity films. So these are candidates for these process to happen. And we actually looked at satellite images to try to find these filaments across the globe. We focused in the boreal spring, and we were very happy to find these filaments in the Black Sea, in the Bay of Bengal, and in the Sea of Japan or East Sea. And these filaments seem to be on the edges of mesoscale structures. Uh, these ones, I really like these ones. And this shows that this process can possibly be happening across the globe, and it might be responsible for SST and ocean heat uptake biases in numerical simulations that don't resolve these mesoscale salinity fronts. And so to wrap up, I would just like to again tell you the final remarks of this presentation. The three main things to remember are that warm waters can converge as salinity fronts. They form these temperature anomalies that can exceed 1 degree Celsius. These SST anomalies are going to cause RC heat flux submesoscale anomalies. And these anomalies are happening in a place where we wouldn't expect RC heat flux anomalies, which are salinity fronts. And lastly, these filaments, they also support downward vertical heat transport, which is the opposite of what's observed on temperature fronts. And with that, I'd like to thank you guys and open up for questions.
Great presentation, Caique. So now we are open for questions. If you want, you can unmute yourself or put the comments on the chat. I do have one question. I actually have many questions, but one of the things that I was thinking is, so if you can go to slide 23, and maybe this is obvious, but like I'm very curious about the asymmetry in the Rossby number for the panel F. And so usually when you have warming for some mesoscale processes, I mean for positive Rossby numbers, you have a negative temperature anomaly for the negative Rossby numbers, and I was wondering what could be that, and what could explain the cooling that you have around the beginning of July.
Uh, you mean the cooling I have here or the cooling I have
Yes,
here?
yeah,
The
for
cooling.
high Rossby numbers, yeah,
Yeah, okay. So here I think so this is a period where again the winds um
or higher.
the winds are higher and the vertical heat fluxes are not imposing a lot of heat here. So and besides the winds being higher, there was also cooling in the it was net cooling instead of net warming. So I think that might be part of the story here. Um, but yeah, if you look, for example, the VHF here, there's
Mm.
more cooling than warming, and then the advection, there's not a lot happening in this time. So I think maybe that's the reason. But yeah, I haven't looked much into that specifically. But yeah, that's a good question.
Um, Megan Cronin, can you
Yeah.
unmute yourself?
Yeah. Great talk. One of the last slides you had was the global map of that normalized R and Q. R was the salinity front and Q was the normalized heat flux.
Yeah.
And I look at that, it's like there's this, the equator is a boundary for this. And I'm kind of surprised that it's actually on the equator. I mean, it makes it seem like F is coming into play as opposed to, say, the ITCC, the thermal equator, which is north of the equator. Can you explain what's going on right there at y=0?
Yeah, that's a good question. One thing I would say is that like this map is just looking at the salinity fronts, but it's not actually telling us if these are submesoscale salinity fronts. So even though we have something showing up in the equator, uh, it's kind of hard to define the submesoscales in the equator, and I don't know if this would be very appropriate, but that being said, yeah, yeah, this line is very interesting. I don't know if it's because some of these places have more salinity fronts when there's more rain, or there's like a more rivers are applying here. Yeah, true answer is that I don't know. It is very interesting how it pops up in the equator. That's a good point.
Yeah. Um, I mean, I would have expected it off the equator, like
Yeah, it should be more. Yeah,
south
yeah,
of the ITCC or something, on the edges of the ITCC, but it seems
yeah,
to be dynamically linked here to the equator.
yeah.
Okay.
Thank you.
Interesting. Thanks.
Lisan?
Hi, it's a really nice talk. Thank you. I have two questions. The first one, especially the last page, you summarized that those filaments could induce those lead-sensitive fluxes anomalies. So, and these anomalies associated with warm fronts, right? Just wondering, is to my understanding, is kind of your experiment is kind of fluxes, is kind of forcing. And so this anomaly is basically is at ocean's effect in those like filament effects on the atmosphere. Does atmosphere respond to anomaly? If so, do they feed back to it? If they feed back, they could kill those anomalies. Is it right? So how experiment do about those feedback interaction between the atmosphere and the ocean?
Yeah, yeah. Unfortunately, since our model is not coupled, we couldn't see what would be the feedback in the atmosphere. But yeah, that's something really fun to do. See what's the feedback. I think uh, Igor that's presenting next week or soon. Uh, he talks about how like these latent heat fluxes they can kill they can extract energy from the ocean and kill the reduce the strength of fronts. So I think I think you have a really good point, but unfortunately we couldn't see the how
It's
what
okay. Yeah.
yeah
Yeah, so probably your model right now is one side, just like forcing how the give the forcing and see how the ocean responds. Is that kind of experiment?
uh So can you repeat the last
I
part?
mean, your model right now cannot diagnose the feedback interaction, the two-way feedback interaction. Yeah, that's okay. I just wonder whether that conclusion is because it just diagnosis, or it just like you actually your model can simulate those kind of effects. But that's okay. I understand this kind of mostly is diagnostic results, and mostly is from the SST effect. So my second question is, I mean, you show the salinity front and the temperature front. What's the density ratio? Is this a front density compensated front? I mean, or is salinity driven? Or I mean, you only show a few cases that is the temperature fronts associated. That at that time, at that kind of spatial scale, means like a submesoscale, is temperature salinity compensated?
Yeah, it's so when we computed the Turner angle for the horizontal Turner angle for the shelf, it's mostly salinity driven. And when the salinity, when the warm filament forms, you actually reinforce the gradient because you have the warm water on the fresher side and the colder water on the salty side. So you reinforce the gradient, but they're mostly driven by salinity here.
So the most driven by the salinity, but at these locations, you also see the temperature change along the salinity driven fronts, and that is why you see the fluxes. So the fluxes is response to the temperature fronts associated with salinity fronts.
Yeah. It's just the temperature front is like a difference of 1 to 2 degrees Celsius, but the salinity front is way stronger. It's like I think it's order 5 PSU or something. So the salinity front still dominates when we compute the Turner angle.
Okay, so if you compute the temperature, I mean those like a density ratio RO, probably can show how those like a composition.
Yeah, that's something. Yeah, that's something I could do more explicitly too. That could be interesting.
Thank you. Yeah.
Thank you.
Chidong?
Yes, could you please go back to your slides showing the diurnal cycle of the vertical profile with the surface wind on the top? Yeah, this one. Yeah, here. If I read this correctly, on the bottom, the blue color is the nighttime and the red color is daytime.
Yeah.
So in that sense, you have this interesting surface wind diurnal cycle, but it shows maximum at night and the minimum at daytime. This is the opposite from what I would understand. So based on my atmospheric education, surface wind should be strong during the daytime and weak during nighttime. So this is opposite. Could you explain that?
Yeah, so this region, so this diurnal wind variability is because there's a strong land sea breeze in the coast. I can't remember now if the land sea breeze is more intense at night or not. But yeah, that's a good.
Yeah, I that's what I thought is could relate to the land sea breezes, but in many places the land breeze is weaker than sea breeze.
Okay.
Yeah.
Yeah.
So this demonstrate the land breezes are stronger than sea breezes. So
yeah.
So I'm just trying to understand this.
Cool. Yeah, that's a good point. I didn't think about that. I can look more into that.
Okay, thanks.
Thank you.
Sarah?
Yeah, really nice talk. I'm wondering about resolution questions. So you've done the SST using high resolution infrared SST, which meant that you found days when it wasn't cloudy. What are the limitations if you needed to use microwave SST? And And I think the same question applies for thinking about global models. A lot of the Earth system models are run at pretty coarse resolution, and nobody's trying to get at the submesoscale. How much is that a problem?
Yeah, I try to look at some microwave satellite data. I couldn't see anything. I think it depends on the region, like on the radius of deformation, if the microwave is gonna get anything or not. But yeah, these maps, like these filaments, they're at least in the simulation and in the Gulf of Mexico, they were 5 kilometer width. So if the microwave resolution is it like a 10 kilometer? I don't remember.
25, yeah, 15 is what people aspire to.
Yeah, so for these very narrow filaments, you couldn't see them on the microwave. And
Yeah.
for model resolution, again, if you're here, we're in a case in the shelf where the radius of deformation was around 4 or 5 kilometers, and if we for our 2 kilometer resolution, it was still like kind of it wouldn't fully resolve the submesoscale, so we couldn't form the filaments too. So for most Earth system models, if that's if they're not resolving fully until like past the radius of deformation, I think you also cannot get them. Like I don't know if you would get it even in like the LLC simulation.
Yeah, it's a good question. And an interesting question about budgets and the impact on the overall budget.
Yeah.
Well, lots of food for thought.
Yeah.
Thank you.
Thanks.
Ram?
Hey, this is actually Alex Korabov. So there's a number of us here calling from NOAA. Thank you guys for very interesting talk, very stimulating. We understand that computing the term balance analysis, especially doing it by post-processing of high-resolution model like ROMs, is a difficult business. Did you compute all the terms, and what was the residual?
On the heat budget term, yeah. It was difficult doing it offline. There was a residual. When I compare,
like 100%, 10%. If you take your tendency minus whatever is on the right hand side.
Yeah, my tendency minus the net. I didn't compute what was the percentage, but like we saw that qualitatively the trends were really similar. But we think most of the residual is because we're doing the budget offline. And also I didn't explicitly include the penetrative heating here. So some of the residual is because of that. But I did yeah. Go ahead.
Yes, especially when you like do advection term. When you do like total advection, it's like 2000 watts per meter squared. When you do separately horizontal and vertical, it's 20,000. It's like one order of magnitude larger, right?
Yeah.
So basically, you kind of take the difference of very large quantities. So I think it would be tremendously for us. It would be interesting to see what is actually the residual there. So how much we can trust those analysis.
Yeah, it was difficult, and the reason I used the full advection instead of breaking it when I'm doing the actual budget is because there's a smaller residual if I use this one. Yeah, it is difficult to construct the budget with ROMs offline.
Well, did you try to use just outputs, turn balance outputs from ROMs?
Unfortunately, we didn't have the flux terms saved in the simulation, and this was run years ago by previous PhD students, and couldn't get those. But again, we did compare the net with the tendency, and the trends were really similar. So we think this is representing the process.
All right. Yeah. yeah. But again, thanks. It's very interesting talk. Thank you.
Thank you. Thank you.
Igor?
Hey, Caique, awesome talk. I was wondering, like we've talked about this before, how like our works converse a lot on like the same salinity fronts being the opposite and trying to do different things. Have you looked at like how is precipitation playing a role in the results? Because I think there are like dry lines and a lot of atmospheric mechanisms in the region that you're looking at that change precipitation a lot. And for the region that I'm studying, the California current is well known for not having that much precipitation. And then I was wondering if you see as precipitation goes up, do you see any differences in like the general like the formation of warm filaments or like the vertical heat flux?
Yeah, that's something that I've not looked at all, but it sounds like a great idea. Yeah, it would be fun to explore this. But yeah, interesting.
Okay, cool. Thanks.
Thank you.
Any more questions? Yeah, okay, so let's thank Caique one more time. I think it was a great presentation, Caique, and as Igor mentioned, it's well connected with the next presentation that we're gonna have next week. So keep in touch, and thank you all for joining this talk.
Thanks, everyone.
Bye.